Good evening, students. Welcome back to PPS online class. In our earlier session, we discussed the leftover concepts from your fifth unit. We started the concept of order of complexity, and I have given the basic overview related to order of complexity. And in today's session, hopefully, we'll be discussing the remaining thing, and we conclude this fifth unit in today's session, hopefully. So, without wasting time, let's just go to that slide. So here we can review the syllabus. We have completed your basic searching algorithms. We have also discussed the basic sorting algorithms, and I also gave the overview on uh, order of complexity. And we said to analyze the performance of algorithms, we need the complexity of an algorithm analysis. And for that, we said we have different notations. Uh, and in today's session, hopefully, we will discuss those notations. And before that, some of the topics like necessity of analyzing an algorithm through complexity that I have given in my previous session, earlier session itself. Let's just review that one and we'll discuss the remaining topics. So quickly, I will take you to that slide where we started the order of complexity. This is what we said. Algorithms, they are fundamental to computer science. Many problems can be solved through algorithms only. First we write the algorithms, then only at the designing stage, then only we said it can be converted as a working program. And we discussed many properties of an algorithm, and then we went to performance analysis, and we discussed some of the things under it as well, under this as well. We said we mostly focus on space complexity and time complexity thing. So we said space complexity is nothing but the amount of memory needed to the program for completion, and time complexity is nothing but the time complexity or the time required for an algorithm to complete, or the time required for a program to complete its execution. So uh, on what basis we analyze the algorithm? We have different criterias, or we have different parameters. On that only we are going to analyze the algorithm. The first is the time criteria, and the second is the space criteria, network consumption, power consumption, and finally the CPU registers. So we said we mostly focus on the top two, that is time and space criterias for an algorithm whenever we do the analysis. Uh, when we say an algorithm as an efficient one, that means it is consuming less time. That is nothing but it is faster when compared with other algorithms, other similar algorithms. It should be faster. Then only we call it as an efficient algorithm. Okay. So when we calculate the time criteria, when we analyze the time criteria for an algorithm, we said it is not going to be in the form of watch or clock time, rather it is going to be a time function. Same thing for space, it is not going to be in megabytes or gigabytes that the algorithm consumes. The algorithm consumes the memory as the algorithm consumes the memory, but rather it is going to be a space function. Okay, time and space functions we derive, and based on that only will analyze the algorithms. Okay, so yes, how we measure the analysis time and how we measure the space. This also I gave some idea on that day. So every simple statement which is executing exactly once in your program, if it is not nested or if it is not repeating itself in an algorithm, we said it will take only 1 unit of time. Okay, a normal statement, a normal simple statement in your program will take 1 unit of time for its execution. Okay, and if we have a repeated statement or if we have a recursive statement, then the concept will differ. Okay, it will consume more than 1 unit of time, and when it comes, we will discuss how much units it will consume. Then space analysis, same thing, a simple variable. Okay, a simple primitive type of variable will consume 1 word of memory or 1 unit of memory also, we can say. Okay, 1 word of memory. And if it is complex variable like your array or your structure, your pointer, anything, if it is not primitive, if it is derived or if it is complex variable, obviously it will consume more than 1 word of memory. Okay, so yeah, here we took the simple algorithm for swapping two numbers. We know the logic how we swap two numbers. Just we need to take a temporary variable. Okay, the easiest approach we can say, just we need to take a temporary variable, and we need to store the first variable value into the temporary variable, and we need to take the uh, uh, second variable's value into first variable, and then finally the temporary variable value into the second variable. Likewise, we employ our algorithm for swapping two numbers. So if you do the time analysis, we said the first one will consume only 1 unit because it is a simple statement. Same thing for the rest of the statements. As they are simple statements, they will consume 1 unit each. Okay. And when you count this, you got three units. Okay. And as we got a constant value, these 3 units, as we got a constant value, the order of complexity will be 1. Time complexity will be 1, order of 1. So whenever we got a constant instead of a function, for a function, whenever we get a constant value instead of any variables or something in your function expression, then the order will be 1. Same thing for space. We have three variables, a, b, and temp. And as a, b, temp, all three are simple, regular, primitive type of variables. They will consume only 1 word of memory into your computer's memory, 1 word. So, all in all, if you combine all three, you will get 3 words. Again, it is a constant only. Here also, we are getting a constant. So again, the order of the space complexity for this particular algorithm will be order of 1 only. So whenever there is a constant, this time complexity or space complexity or the big O notation, it will go 1 only. Okay. Then we have asymptotic notations. See, whenever we are measuring the time and space complexity of different algorithms, we need to depend on this asymptotic notation because the function representations, whatever we derive, so in order to do the comparison, which one is best, which one is worst kind of thing, we in order to do such a thing, we need this asymptotic notations. Okay, which one is consuming more time or which one is consuming less time, which one is consuming more space, which one is consuming less space. In order to do that comparison thing, we need these asymptotic notations. Okay, so because all these, whenever we do the time and space complexity analysis, they are related to functions, because we already said that whenever we go for time complexity and space complexity representation, we use functions rather than the specific time or specific memory. Okay, we use functions over there. As this functions concept, it belongs to mathematics. Okay, functions, we know that whatever functions concept we have, it belongs to mathematics. So your asymptotic notations, because they are completely dependent on this functions thing. Okay, your asymptotic notations, they are completely dependent on this functions thing. So your asymptotic notations, they are also belonging to mathematics. Okay, so for calculating time complexity, and as we are using functions, um, uh, asymptotic notations, it is also useful in algorithm analysis. Okay, whenever we go for algorithm analysis, the asymptotic notations we use. Yeah, why we use this asymptotic notations? The biggest advantage we can say, to simplify the functions or to categorize the functions, we use this asymptotic notations. Okay, very soon you will understand when we see the definitions of these asymptotic notations. There are three different types of notations we have. The first one is big O notation, then we have omega notation, big omega notation, and finally the theta notation. So we call it as the other names for these notations is your theta notation, the best one. It is average bound. We call it as average bound, and the omega notation, the lower bound, and the big O notation, it is the upper bound. See, what is best among these three in the sense the theta notation is best. If you represent an algorithm in theta notation, your algorithm or the your complexity function will become specific. It will not be generalized. Okay, it will not be generalized. It will go like a specific whenever you go for average bound. But representing a function in average bound, some it is always not possible. Sometimes it is very difficult. So what we do, if it is not possible to represent a particular function in average bound, that is nothing but in theta notation, will go either with big O or with omega. So in most probable cases, we go with big O notation only, the upper bound notation only. Okay, you will understand the upper bound notation. What does it mean by upper bound notation? You will understand. So here you can read one last statement before we move to the next slide. All types of functions we can represent in any of these three bounds. Okay, whatever function expressions we can represent in mathematics, or whatever function expressions we will get when we analyze the algorithms in our computation, every function, every time complexity function or space complexity function, it can be represented in any of these three notations. Okay, what I said, to get this specific notation we have to go for theta, but it is not always possible to get the accurate specification. That's the reason what we do, we'll go with either big O notation or with big omega notation. Okay, so I will explain this particular thing with a simple example so that you will remember this particular concept, so that you can understand this particular concept very clearly. So how these functions works and how these functions helpful in our day-to-day life, in the sense, see, suppose mostly whenever we go for functions or whenever we go for these asymptotic notations which are dependent on functions, we are doing a kind of comparison, or we are doing a kind of prediction. Okay, which one is good, which one is best, based on some assumptions only we are taking here. Okay, nothing is specific, based on some assumptions only we are taking, and by doing that we are analyzing the algorithm. This one is best, this one is underperforming, likewise. Okay, so to understand it, take an example that I want to buy a mobile phone from the market. Let us assume like this, I want to buy a mobile phone from the market, and we know in the market we have different options. Whenever we go for purchase of mobile, we have different options, and among the options I cannot buy all, right? I cannot buy anyone that is readily available in the market. What I mean to say, see, one thing which I need to focus is my budget. Okay, based on that budget only I can buy the mobile. So let us assume my budget around 20,000. I want to buy a mobile which is of 20,000 rupees. So I'm asking for recommendation to my friend. Okay, so how he will recommend? So if I don't give the budget to him, how he will recommend? See, he will say, he will give some models which will cost me around 2,000, 3,000 somewhere. Okay, because we know that in for 2,000, 3,000 also we can easily get a mobile in the market, isn't it? So he can suggest that one. Okay, so it is a very okay. Whatever budget I made now, it is very low price, isn't it? To my budget, it is nowhere it is matching. It is very low price, isn't it? So if he is giving such a suggestion, if he is giving such a thing, we consider it as lower bound. Okay, and sometimes this lower bound, it is also not useful. The best example I have already given to you. isn't it? If he is giving me the suggestion of buying 2000 rupees mobile when I already decided to buy a mobile phone near about 20,000, that suggestion is of no use to me. So consider that suggestion as the omega notation. Okay, omega notation. So possibly we can also have mobiles which will cost us like lakhs of rupees. Okay, we have mobiles which will cost around 2 lakhs, 3 lakhs. If my friend is giving that type of suggestion to me, okay, go for a mobile which is costing like 2 lakh rupees in the market. Again, that type of suggestion is also useless to me, isn't it? So consider that as the upper bound. Okay, sometimes that will also go useless because they are not specific, they are generalized things, isn't it? There is no guarantee that your upper bound will have the result, and there is also no guarantee that your lower bound will have the result. But when it comes to the average bound, the specific bound, if he says exactly go for a mobile which will cost you around 20,000, okay, so immediately you will show the interest in that suggestion and you try to follow that suggestion because it is looking somewhat useful to me, because it is falling under my budget, isn't it? So that type of notation, if you are giving for your algorithm, obviously it is of useful. But in the real time, there is less probability that my friend's suggestion will match with my budget, isn't it? There is less probability. So what we do, instead of going with average bound whenever we can't find the perfect match, what we do, we go with either upper bound or with lower bound, which matches nearest, okay, which is not matching exactly, but at least nearest to my uh, assumption. I mean, whatever I said, now I need to buy a mobile of 20,000. If my friend is suggesting nearest in the sense around 18,000, lower bound you consider. Lower bound in the sense below 20,000. Below 20,000, it should be near to 20,000. Then only I will consider. If it is too low, obviously I will reject. If it is somewhere around 18,000, 19,000 also, there is a possibility that I may accept that. So that's the reason. Instead of getting the specific theta, what we do, we go for lower bound or upper bound. And if my friend is suggesting around 21,000, 22,000 also, what I will try to increase my budget and I will try to buy that mobile. There is a possibility. So that kind of suggestion also, there is a possibility that I will accept. Upper bound in the sense, not just the exact match as well as the above match. Okay, so very soon you will understand. No? Likewise, this particular example you just keep in your mind when we study the Bigot notation, theta notation, and omega notation, because it is somewhat from your analysis of algorithms. So it is, I mean, your skills, your skill set, whatever you acquired so far, it is not sufficient to understand this concept. Okay, you need to work more on these particular things to understand. Okay. So here we have the notation, Bigot notation, the upper bound, what I said, upper bound. So what it is, the definition, if you see, if we have a function f of n, okay, f of n, it can be represented as order of g of n, if and only if, we call it as if and only if, double f in the sense, we read it as if and only if. Okay, so once again I'm repeating, if we have a function f of n and you want to represent that function in upper bound, order of, we call it as order, okay, order of g of n, when you can represent if and only if there exist positive constants, two positive constants, such that C and N naught, such that two positive constants C and N naught, such that f of n is less than we are saying less than or equals to, f of n is less than or equals to C multiplied with g of n. Okay, C multiplied with g of n for all n greater than or equals to n naught. Okay, for all n greater than or equals to n naught. If you have such a representation. If such a representation is possible, then we call f of n as order of g of n. If such a representation, I mean, you're having a fixed value, you have a some assumed value in your mind, and your friend is giving above values. Okay, above values. So when you can apply those things, I mean, when you can go for such a suggestion, in the sense, if this type of notation is possible. Okay, given function, it can be represented as order of g of n only if there exist two positive constants c and n naught, such that f of n is equals to c multiplied with g of n for all n greater than or equals to n naught. So take an example of that one. So let us assume we have a function 2n plus 3. I'm taking a function 2n plus 3, and that 2n plus 3, it can be represented as 2n plus 3, it is always less than or equals to 10 multiplied with n. So here I took 10, you can take any probable value. So I can't take 2n, isn't it? I can't take 2n. See, if I say 2n plus 3 less than or equals to 2n, obviously this condition will not be satisfied, isn't it? So place 1 over here for all n greater than or equals to 1. Place 1 over here, then what will happen? This will become 5 and this will become 2 only. So this particular condition will fail. So from where I have to start? From 5 I have to start. Minimum 3 plus 2, 5 I have to start. So then 2n plus 3 less than or equals to 5n. From this point on, your equation will go correct. And as you can see, this is your f of n. I have written here itself. This particular thing is your f of n. And for all 5 greater than, okay, for all 5 greater than, this particular thing will become your constant c, and this is your g of n. So now how you can represent this whole thing? F of n is equals to order of g of n for all n greater than or equals to 1. We know that g of n is nothing but n. So represent that n. Okay. So f of n is equals to order of n for all n greater than or equals to 1. Okay. So don't get confused by seeing this 10. You can represent any value. You can represent 1000 also here. In that case also it is true. Okay. That's the reason I said now upper bound, we always try to look for the nearest to our consideration. Okay, it may be 1 crore also. We have mobiles of that category, maybe. We don't know. Okay, so we don't go for that one. Which one we will go? Which is very near. If we are talking about upper bound, whatever our assumption is there, whatever our consideration is there, if it is really close to it, nearly close to it, then only we will go for it. Okay, if it is not a perfect match, if it is not theta, if it is omega, sorry, not omega, if it is big O, then which one we select, ma? In the upper bound, whatever is near to us, that only we will select. Okay, will not go to the rest of the one, even though all will satisfy. Even though here you keep 1000, here you keep 10,000, all such constants will satisfy my expression, but we will not go to that one. We'll look for the best, the nearest. Okay, likewise. So here you can take another example. See here, for this also, we can even make 5n square also over here. In that case, what will be my order? F of n is equals to big O of n square. It will go like big O of n square. So for this also, my expression, it is becoming true. As you can see, 2n plus 3. If I put 1 in this place, then what will happen? This will become 5 and this will also become 5. So 5 less than or equals to 5. I said equals to also. So condition true. If I put 2, then what will happen? Here 2 2's 4 plus 3 7, and here 10, isn't it? This is no, not 10, 20 I guess, because 2 power 2 it is 4, 5 multiplied with 4 it will be 20. So this is 20 and this is 7. Okay. For all n greater than or equals to 1, this condition is becoming true. So I can, this is your f of n, this is your c, and this is your g of n. So I can make this f of n, I can make this expression as f of n is equals to order of n square. Okay. So here this f of n, see we have the what we call function classes, something like this. We have all the function classes, what possible expressions I may get in terms of big O notations or omega notation or theta notation. what probable notations or what probable function classes I may get that I have kept over here. So if it is a constant, we know that we will get order as 1. Okay, whenever the supplied expression, supplied value is a constant for a function, immediately the order we go will become 1. So that category, that class I kept over here. Likewise, n we got for the previous example. Likewise, these are all n square also we have seen here. So likewise, these are all possible classes of functions. So in that, the perfect match for your given function will become average bound, and whatever upper values, okay, for this 2n plus 3, the perfect match we said the average bound, and whatever upper values we have, n square, n cube, 2 power n, 3 power n, n power n, all that will satisfy my expression. But I will not go for all that, isn't it? I will always look for the closest, nearest, which will satisfy my expression. Okay, so this average bound we will consider, and all the upper bound will also satisfy, but we will not consider. Okay, when we are talking about upper bound, obviously the lower bound will fail. As you can see here, for f of n, order of n square, for this function 2n plus 3, order of n square, it is true, it is satisfying. But order of log n, okay, you can take the log n value, and if you try the log n value, it will fail, it will not satisfy, because it belongs to the lower bound. And always your value, okay, 2n plus 3 value, it is less than n log n. Okay, it is that's the reason it will not go true, it will go false. Likewise, order of n also true, order of n square also true. Here we have that. ఓకే, మనం అప్పర్ బౌండ్ అన్నామంటే ఓన్లీ అప్పర్ బౌండ్ లో ఉన్న కేసెస్ మాత్రమే సాటిస్ఫై చేస్తాయి. వేర్ ఎవర్ వీఆర్ గెటింగ్ ది ఫంక్షన్ వాల్యూ, ఆ ఫంక్షన్ వాల్యూకి అప్పర్ బౌండ్ లో ఉన్న అన్ని వాల్యూస్ సాటిస్ఫై చేస్తాయి. బట్ ఇట్ డజంట్ మీన్ దట్ విల్ గో విత్ ఆల్ దట్ వాల్యూస్. విల్ ఆల్వేస్ లుక్ ఫర్ ది క్లోజెస్ట్. సేమ్ థింగ్, ఓకే, big O notation, the opposite. Big O notation, big omega notation is the opposite to your big O notation. Here, simply this symbol you can see. Previously it was less than, but now it became greater than. Our function value should be greater than on all cases. Okay, so here my function f of n I took as 2n plus 3. So 2n plus 3, it is always greater than 1 multiplied with n. Okay, for all possible values of n, including 0. Okay, you can keep any value over here, and you can see your function will always become greater than this particular thing. So this you can consider it as c, and this you can consider it as gn, and this you can consider it as fn, f of n. So you can write your expression function f of n is equals to omega of n. Okay, now omega of n. So omega here, it means lower bound, not just n. Whatever possible values we have, whatever possible function classes we have, below this n, all that will satisfy this particular function. Okay, all they will satisfy this particular function. As you can see here, omega of n, it is going true. Omega of log n, it will also go true. But if you try any function class from upper bound, if you consider any function class for upper bound, because these two belongs to the lower bound, we got the true here. And if you try with upper bound, obviously it will go false. And here I made that statement, always the nearest matching function is useful and has to be selected. Okay, so always we try for the nearest matching. Will not go for other possibilities. Okay, so for our omega and for our big O, when we consider the upper bound and when we consider the lower bound, in both the cases, n is satisfying best. Order of n or omega of n is satisfying the best. So we are selecting that one. Okay, so wherever we are trying for the upper bound, not just order of n, but whatever above functions, above class functions we have, all they will also satisfy my expression, but I will not go with that one. Again, same thing, whenever we are trying for omega, whenever I am trying for omega notation, as it is the lower bound, not just omega of n, but whatever function notations we have below omega of n, all that will also satisfy, but I will not go for the other ones, because my omega of n is the best satisfied. Hopefully you understood. Best satisfied or the nearest to my approach. Okay, hopefully you understood these things. So lastly, we have the theta notation. We call it as average bound, the exact match. Okay, whatever representation we will give under this theta, only that will satisfy. If you try the upper bound, that will also fail. If you try the lower bound, that will also fail, because here we need to satisfy both. As you can see here, the definition of theta notation, the f of n, the function f of n, it can be represented as the uh, order of, sorry, not order, theta of g of n. It can be represented as theta of g of n if and only if there exist positive constants. Here we are looking for three different types of positive constants: c1, c2 and not n0. c1, c2, n0, such that here you can see c1 multiplied with g of n, it should be less than or equals to f of n. It should be less than or equals to c2 multiplied with g of n. ఇక్కడ 2 times రావాలి g of n. ఇక్కడ కూడా సేమ్ అదే రిప్రజెంటేషన్ రావాలి, ఇక్కడ కూడా సేమ్ అదే రిప్రజెంటేషన్ రావాలి. Then only we can represent this function f of n in theta. Okay, theta of g of n. Okay, as you can see here, our function 2n plus 3, we already calculated the best lower bound value, and we also calculated the best upper bound value. Okay, the nearest upper bound value, that only I am placing here. The best nearest lower bound function is, lower bound notation is 1 multiplied with n. The best upper bound notation is 5 multiplied with n. Simply consider this 1 as c1, this 5 as c2, and this n will become g of n. So my function f of n, it can be represented as theta of n. So when you are representing your function like this, theta of n, you can try with any other function class, both from your lower boundary as well as from the upper bound. Okay, you can find that only for the order of n, only for that average bound, your function is true. Okay, f of n is becoming theta of n. But if you try with other possibilities like n square, if you try with n square, then what will happen? This lower bound will fail. Only upper bound will be satisfied, but lower bound will fail, isn't it? Same thing if you try for any other function class from the lower bound, that is order of n log n. We know that order of n log n will be satisfied only for the lower bound and will not be satisfied for the upper bound. Okay, so when you have represented your function notation using theta notation, only that specific representation will satisfy your function, and rest of all the function classes, both from upper bound as well as lower bound, they will not satisfy. They will simply go false. Okay, so that is the reason will not go specific, because there are other problems we'll get if we represent the specific notation. So we always go for big O notation. Okay, big O notation only we will go, that is the upper bound. Okay, big O notation or upper bound notation only we will use. Okay, see, always what we have to do, we need to try for theta notation first. But if you fail to represent a function in theta notation, because always I said na, sometimes it is also not possible to represent your function under theta notation. So simply what we do, if it is not possible, we'll go for big O or big omega. Okay, big O or big omega notations. Upper bound or lower bound representations we will take. Hopefully it is clear. So now we will do the analysis of different types of algorithms using frequency count method. Simple statements unte analysis very easy ma. Always if in your algorithm all statements are sequential, let us assume all statements are sequential, and if you know the exact number of statements in your algorithm, a constant value you will get when you count. So obviously your complexity function will become a constant, order of 1, the smallest function we can say, order of 1. But in real time we didn't encounter any such functions, impractical algorithms. Rather, we'll get more complex algorithms in nature when we go for real-time analysis, real-time space and time complexity analysis, isn't it? So this particular thing is the best example. So here what I'm doing, I'm trying to identify the sum of an array of elements. In this array, how many items we have? N number of items. So nothing is fixed over here. N number of items I have. So I'm simply trying to calculate the sum of that n items. Okay. So we know that the procedure, initially we need to take a temporary variable, some variable, and to that we need to assign 0. Then as array elements we need to process through indexing. So we will take a loop over here, for loop తీసుకుంటున్నాను, and in that for loop we know that for I equals to 0 I must be less than n I plus plus. So here we need to do a kind of analysis. Whenever we are saying I equals to 0, this initialization inside the loop, we said it will happen only once. Okay, inside the loop మనకి ఇనిషియలైజేషన్ ఎన్నిసార్లు జరుగుతుందమ్మా? ఓన్లీ వన్స్ జరుగుతుంది. Okay, and when we talk about this termination condition check, this condition check, how many times it will occur? N plus 1 times, because from first iteration till last iteration, and before it exits from the loop, at that time also termination condition will be tested. When the failure case, okay, when the termination condition becomes fail, that particular case also will be considered. So ఒక లూప్ లో మీకు టర్మినేషన్ కండిషన్ ఎన్ని సార్లు ఎగ్జిక్యూట్ అవుతుందంటే n+1 సార్లు అని చెప్పాలి. సింపుల్ గా స్ట్రైట్ అవే n+1 టైమ్స్, because the failure case also we need to take into consideration. So how many times your termination condition will be tested? n+1 times your termination condition will be tested. And finally the updation, how many times this updation will be done? N times. If this loop is repeating for n number of times, then your updation will be done exactly for n times. Okay, so these three statements I have given how many times they will execute, and when you have such a thing, always take the maximum. Okay, no need to take the sum, always take the maximum. And between 1 n+1 n, we know that n+1 is maximum. When we do the time analysis, this particular statement s equals to 0 will be executed only one number of time, exactly one number of time. But when you consider this loop representation here, loop signature, this signature, in this signature, this first statement only once, second statement n+1 times, third statement n times. So take the maximum, that is n+1 out. So this particular thing, how many times all in all will be considered? n+1 times all in all it will be considered. Then inside the loop body we have the summation statement, which will calculate the sum of all the items in an array. And we know that we don't know how many items we have inside this array so far, because as you can see the size here, n it is saying, not specific. Okay, so this inside loop, whatever statements we will have, how many times they will execute? N number of times they will execute. Okay, so simply mention it as n, and after this, as this return s, it is out of the loop body, so it will be executed only once. Okay, now add all these, so what will be your value? 2n plus 3. As you can see, 2n plus 3 you will get. So this, so many times we practiced in our upper bound, lower bound and average bound considerations. This particular function we practiced so many times, and we clearly know that this can be represented in order of n. Okay, wherever you have such a thing, simply take the order on the variable only, because constants will become 1 only. So take the order on n only. So order of n, the representation of this notation of this function is order of n. Now space complexity analysis, again here, how many number of items we have inside this array? It is not fixed. So array is n number of items, as it is not fixed, n number of items. But inside this n, because to store the value of, to store the size of array, we are taking n. So that n variable, it will consume one word of memory. To calculate this sum, we are taking another variable s, it will also consume one word of memory. and I variable also we have, it will also consume 1 word of memory. And if you add all these, what you will get? N plus 3 you will get. Again here this 3, it is a constant, so it will become 1, and n, it is a variable, so order of n likewise. So if any statement is repeating for more than one, how many times we don't know, unknown number of times, the frequency of execution of that statement will be calculated. Okay, so ఎన్నిసార్లు రిపీట్ అవుతుందో మనకు స్పెసిఫిక్ గా తెలియనప్పుడు we simply represent that thing with n. Okay, we simply say n number of times it is repeating. If we don't know how many exact number of times it is repeating, we represent it as, we call it as n number of times it is repeating, and your function specification, your function notation will also come in that repetitive terminology only. Okay, hope you understood how we represented order of n for time complexity and order of n for space complexity here. Okay, then we have another example. This is something matrix addition ma, when you add two matrices of size n. Okay, okay, of size n. Here both number of rows, number of columns, I have n only. Okay, n number of rows, n number of columns, and we don't know how many times this outer loop will iterate, and we don't know how many times this inner loop will iterate. So we know that this is exactly once, this is n plus 1, because the false case also it will be considered, and this is n. Here also same thing, this is 1, this is n plus 1, and this is n. Okay, so from this what we took, n plus 1 we took out, because this is the maximum. And inner loop, how many times this will iterate ma? Because it is a nested loop, so this thing, it is dependent on the outer loop as well. So this thing, this whole loop will get repeated n number of times. So n multiplied with, and how many times this inner thing will get repeated? n plus 1 time. అంటే ఈ లూప్ ఇన్సైడ్ ఉన్న లూప్ అవుట్ సైడ్ లూప్ కూడా ఎఫెక్ట్ చూపిస్తుంది. సో అవుట్ సైడ్ లూప్ ఈ ఇన్సైడ్ ఉన్న లూప్ ని n టైమ్స్ రిపీట్ చేస్తే ఇన్సైడ్ లూప్ తనంతటకు తాను n plus 1 టైమ్స్ రిపీట్ చేసుకుంటుంది. సో దట్స్ ద రీజన్ n into n plus 1 టైమ్స్. And innermost statement, nested loops lo unna innermost statements, how many times they will get repeated? N into n, because outer loop n times, inner loop n times, so n multiplied with n. Okay, so likewise, so this is n plus 1, and this is n square plus n ostundi ikkada, and this is n square. So how much value? 2n square plus 2n plus 1. Our function 2n square plus 2n plus 1. And if you take the order, it will be order of n square. Okay, like this you will get. If you take the order will be order of n square, big O notation. Then space complexity, as we don't know how many items, because it is number of rows not fixed. So number of rows n, number of columns not fixed, number of columns also n, number of rows n, number of columns n. So matrix n multiplied with n, that is what I have taken over here. A is a matrix, so n cross n, n rows n columns, so n square. B is a matrix, n cross n, n square. C is a matrix, n cross n, n square. And we also used other variables like n I used for storing the size, that is 1. I used again 1, j I used again 1. So 3n square plus 3n. These two are constants, so our order will become order of n square likewise. So for this particular algorithm, both time complexity will be order of n square and space complexity is also order of n square likewise. Okay, next multiply, you can easily calculate here this particular statement how many times. This is 1, this is n plus 1, this is n. Okay, so here you can see among all three, which one is biggest? N plus 1 is biggest, so I took n plus 1. And this particular thing, how many times? This is 1, this is n plus 1, and this is n, and this overall thing gets affected by outer loop, and times n it will get. So this whole thing times n, that is what I have kept over here. So this whole thing, which is the biggest, n plus 1 is biggest, so I took n plus 1 multiplied with n I2. So this will be n square plus n. Lastly, this innermost, this inner n multiplied with n, because outer loop will affect on it and this inner loop will affect on it times n. So n cross n, this will be n square. And another loop I'm taking, again here also we know that this is 1, this is n plus 1 and this is n. Okay, so which one is the biggest? N plus 1. And this thing all in all will get affected by this loop as well as this loop. So n times n, this whole thing. So this will go n square, here you can see n square, and from this 3 we can take n plus 1. So n square multiplied with n plus 1. So n cube plus n square. And lastly, the innermost statement will get affected by all three nested loops. Okay, outer loop n times, second loop one more n time, the innermost loop one more n time. So this innermost expression will execute exactly n cube number of times. So that only I took here, n cube. So overall, this if you calculate, this will become n square multiplied with 1 with n cube, and n square multiplied with 1 n square. Likewise we got. So now 2n cube, because here 1 cube, here 1 n cube, 3n square, 1, 2, 3, 2n, 1, 2 plus 1, like this we got. So now the order will be here, it is not square, it is cube. Order of n cube we got now. Okay, and here also S of n, as you can see, it is a two-dimensional array. So actually this has to come here and this has to go here. I mentioned it wrongly. This will be n square only. Space complexity order of n square and time complexity order of n cube likewise. Hopefully you understood this thing. So now see, every time in every function, whenever in every algorithm analysis, whenever we get a loop, this particular thing we are getting the maximum n plus 1, and this we are getting 1, this we are getting n, and innermost statement gets executed n times and chaptunnam. So this analysis, whenever you have this loop body thing, no need to do the analysis of this one any further, because straight away it is clearly dependent on the inner statement. After doing those many examples, we understood that whatever time complexity analysis we are doing, it is straight away dependent on the inner statements. Whatever loop body we have, it is leastly affecting. Okay, so we ignore this one, we don't do any analysis on this one, we straight away go and we see only the inner statements, how many times they are getting repeated. So as you can see, this inner statement, it gets repeated n times, our order is becoming order of n. Hope you understood this. Here another algorithm. Again, no need to consider this whole, simply remember, and as you can see, this inner thing, it is going in reverse order and gets executed how many times? N times. So our order will be order of n. Okay, take another algorithm. Here I plus 2, even you are jumping 2 times, 3 times, how many times you are jumping, instead of iterating through each statement, or instead of taking each range of value. ఓకే, మీరు ఇన్ఫినిటీలో 0 to అన్నోన్ వి కన్సిడర్ ఇట్ యాజ్ ఇన్ఫినిటీ. మీరు ఇన్ఫినిటీలో ఇన్ఫినిటీ దగ్గరికి 1 హాప్ చేసుకుంటూ వెళ్ళినా, ఒక నంబర్ని జంప్ చేసుకుని 2 హాప్స్ చేసుకొని వెళ్ళినా ఇన్ఫినిటీని రీచ్ అయ్యే పాసిబిలిటీ ఉంటుందా? 3 హాప్స్ చేసుకుంటూ వెళ్ళినా ఇన్ఫినిటీకి రీచ్ అయ్యే పాసిబిలిటీ ఉండదు. ఇన్ఫినిటీ ఈజ్ ఆల్వేస్ ఇన్ఫినిటీ. అన్నోన్ థింగ్ ఈజ్ ఆల్వేస్ అన్నోన్. సో ఈవెన్ ఇఫ్ యూ ఇగ్నోర్ దిస్ వన్, okay, this statement, if you fix the n, how many times this inner statements will get executed? Because half of 2 hops we are taking, instead of single hop, 2 hops we are taking, multiple hops we are taking. Okay, so now n divided by 2 times this inner statement gets executed. So your function will become f of n is equals to n divided by 2, and this you can, n divided by 2 ni manam ena rayochu, 1 by 2 multiplied with n, and this thing as a constant, it will go 1 multiplied with n, it is n only. So your order of complexity will become order of n only. Hope you understood. So again, here simple thing, instead of looking at this thing and this thing, straight away we can go and we can check the inner statement, and as this inner statement gets affected by both of the loop, outer loop and inner loop, outer loop affects n times, inner loop affects n times, so the overall times the inner statement gets repeated n square. So straight away you can write your order of complexity as O of n square. Okay, yeah, it is a somewhat different example because as you can see here, j is less than I we are saying. So your inner loop counter is affecting the outer loop counter is affecting the inner loop, how many times it has to repeat. So when I value is 0, inner loop will not repeat itself. It is 0 times repetition. When I value is 1, the inner loop gets repeated 2 times. When I value is 2, the inner loop gets repeated 2 times. When I value is 3, the inner loop gets repeated 3 times. Likewise, it is moving. Okay, likewise, it is going. And to get how many times the overall loop gets executed, the overall inner statement gets executed, what you have to do? You need to sum all these things. You need to sum 0 plus 1 plus 2 plus 3 plus and so on plus n. దీన్ని మొత్తంని కౌంట్ చేయాలి. So we know that 1 plus 2 plus 3 and so on n, we have a formula n into n plus 1 by 2. Simply apply this formula, you will get the solution. Okay, now calculate n square, this whole thing, n square plus n by 2. And here what will be the order? So just separate this 1 by 2 of n square plus n. This is a constant, will get removed, and the highest possible order of n square. Like this you can get the time complexity, order of n square. Okay, so some of the summary we have taken, summary of time complexity function. If it is a simple loop without nesting, if we have such a thing like this where I gets repeated n number of times, our time complexity will become order of n. Okay, if we have such a thing, 2 hops if we are taking, then also order of n only. If we go in reverse, initialize I to n and decrement I by 1 every time, then also order of n only. If you have such a thing, I equals to 1, I less than n, I equals to I multiplied with 2, okay, then your complexity will become order of log n to the base 2. Multiplied with 3, order of log n to the base 3. Okay, I initialize to 1, I less than I greater than 1 and I equals to I divide by 2, then also order of, simply this is the reverse of these. Okay, this is the reverse of these two are reverse to each other, we can say. In that case also order of n log n to the base 2, likewise you will get. So we know that order of 1 for all constants we will get, order of log n logarithmic, order of n linear, order of n square, quadratic, cubic, exponential. All these are exponential function classes, whatever function classes we discussed now, that only we are talking here. So for any function, if you have the constant representation, your order of complexity will be 1, order of 1. And for any function of order n, your order of complexity will be n only. Okay, when you have 2n plus 3, 500n plus 700, n divided by 5000 plus 6, for all these the order of n is n only. Likewise you can consider. So here we have given the representation of all our functions, which one is less than, which one is greater, kind of thing we have given, and this is the graphical representation. Okay, this analysis and all, it is dependent on your higher semester subjects. There you will understand more clearly what is meant by this graph and why we got these values here. This is beyond the scope of your syllabus. Okay, we just need to understand whenever they give some kind of thing. Okay, so I will show you, because mostly they will ask this only, this particular thing only, as you can clearly see here. Okay, insertion sort algorithm, what will be the time complexity? Likewise they will ask. Okay, how many times this declaration gets repeated? Declaration 1 time. Okay, and how many times this thing gets repeated? This is 1 time, this is n plus 1 time, and this is n time. So all in all, here you can take n plus 1 common, because n plus 1 highest. Okay, for rest of the things, this is a normal statement inside a loop, so n times it gets repeated. This is also a normal statement inside a loop, n times it gets repeated. And this inner loop, how many times it will get repeated? Nothing is fixed here. What is temp, what is walk, okay, till how long these conditions will be true, it is nothing is fixed over here. So we consider this also as n, but outer loop is also affecting on this, so multiplied with n likewise. And inner loop here, this will be n multiplied with n only. This also n multiplied with n only. So overall what we will get? 1 plus n plus 1 plus n, n, n. Here also n square. This is n square. This is also n square. And this last statement, it will also execute n number of times. So keep n. So now as you can see, whatever number of items we have, whatever number of n's we have in this one. So if I write this one, 3n square plus around 5n, 5n plus 2 constants we have plus 2. Like this we will get our function f of n, we will get like this. So we just need to represent this function in big O notation. Order of what will be the highest order of n, that is n square. Like this you can represent. For insertion sort, what will be the order? Order of n square. Here another sorting selection sort we have. It is also very easy. Okay, for all sorting algorithms, it will be order of n only. So here also we will get this is n, this is n square. Okay, forget about the rest of the things. Okay, forget about the rest of the things because the highest order we got, that is n square. Okay, and the innermost statement, it will also get executed n square number of times only. So our order will become n square. But for your exam, it is better if you show all this. This is 1, okay, this is n, this is n square, this is also n square, and this is as it is out of the inner loop, this will also gets repeated n times. Now write the function f of n equals to how much? How many n squares? 1, 2, 3. 3n squares plus how many n's? 1, 2, 3. 3n plus how many normal statements? Only 1. So it will be 1. So now again, as you can see, 3n square plus 3n plus 1, you can write it as order of n square likewise. Okay. So in this way, whatever algorithms you have, you can get the time complexity analysis for that algorithm. Okay. And based on this, you can take the performance analysis as well. What type of measure we need to take for our algorithm. Okay. Based on this sequence, which one is smaller, which one is larger, what type of measure we need to take for our notation, whether we have to go with upper bound, inside the upper bound what is the best possible, and whether we have to go for lower bound, and inside the lower bound which one is best possible, and average bound, as we said, it is highly impossible, highly impractical to achieve. So always what we are doing, we are going for upper bound, and in that upper bound also the closest possible function we are selecting, closest possible function class we are selecting to give the notation for our function. Hopefully this concept is clear. This is what you need to learn from it. Okay. So with this, I'm concluding your 5th unit. Hopefully we have discussed every single concept, whatever we have in it. So yes, rest of the concepts we will discuss in our offline classes. And from tomorrow, if possible, I will start the preprocessor directives thing in online classes. Okay. Thank you very much, students.